Hello sir, this is Yugesh Upadhyay along with Rusha Bhumagai to demonstrate the mini project we created on the topic procedural terrain generation using Perlin noise. As you can see on the screen, we have defined various functions that communicate with each other to generate terrain data, move through the terrain and plot this generated data onto the viewport or the rendered graphics window. Now to execute our program, we'll use the command python terrain generation.py. This creates a window where we can observe a procedurally generated terrain that is being traversed along the y direction. To achieve this, we have utilized a 2D base mesh plane with no z values and rotated it about 45 degrees about the x-axis and projected it into our view plane using perspective projection. Then, using the Perlin noise function, we have defined the z values for each of the vertices of the triangle within the mesh, which when plotted gives us a continuous terrain. Moreover, what we have done is as we travel along the y direction, every 10 microseconds we generate a new values for the farthest end of the terrain and delete the nearest terrain data that has passed through our view. We achieve this using the GL subdata and of OpenGL. This gives us the illusion that we are traveling along the y direction with no buffer overhead. Similarly, we have also used Perlin factor parameter that can be initialized from the command line argument itself. This Perlin noise factor can be used to modify the amount of distance we travel through the noise space to get our consecutive Z values. So, for a demonstration, if I were to set the Perlin factor from the command line to be 0.02, then our terrain would have a very less variation, as we can see in this rendered window. This is because we are not traveling a huge distance in the noise space to obtain our consecutive z values, so the g values differ a very less amount. However, if we were to set the Perlin factor to be 0.2 instead of 0.02, then our generated terrain would look like this. Here we can see that the g values differ very significantly. This is because we are traversing a large number of distance in the Perlin noise space to obtain our consecutive z values. It looks as if we are looking at our terrain from very far away. Alongside this, we have also used the mouse function of OpenGL to modify our field of view used for perspective projection. So if I were to click my mouse and drag it along the window, I can see that the field of view has been changed. It has been increased to about 110 degrees, where we can see our terrain as a whole. Now if I were to continue dragging it, here we can see that the perspective of our view or field of view is extremely small. We're extremely close to our terrain. So if I were to continuously drag my mouse, then my terrain will look like this. This means that through the mouse function we are able to change the field of view, which means that we are able to obtain various perspective projections of our plane as well.